In the inside atoms, we have the three subatomic particles that are found in distinct and separate regions. The protons and neutrons that are found in the center of the atom, which is called the nucleus. The neutrons have no charge and protons are positively charged, have positive charge. The nucleus occupies only a very little volume of the atomic structure, but it is very dense, very big in mass as compared to proton and electrons. The rest of the atomic surrounding the nucleus is where electrons are most likely to be found, which we call orbitals or energy levels of electrons. The electrons are negatively charged, having charge opposite to proton, and move around very quickly in electron shells or energy levels. The place where electrons are bit around the nucleus are called electron shells or energy levels. The electrons are held within the atom by an electrostatic force of attraction. The electrons inside the nucleus are held, or the electrons, inside the atom. My apologize. Excuse me. Within the atom by an electrostatic force of attraction between themselves and the positive charge of photons in the. Here you can see the diagrammatic representation of an atom in which we have the nucleus at the center, containing neutrons and protons, and regions around the nucleus, which we call energy levels or orbitals, which are held together to the nucleus by the strong electrostatic force of attraction caused by the positive charge of the nucleus of protons. Diagram of an atom. About 1837 electrons are equal in mass to the mass of one proton or one neutron. So that's a very big difference. Means electrons are very much times smaller, very much smaller than neutron, and neutron are a little bit smaller than proton, so we can write it in here. So that's the mass difference in different elementary particles of the atom of any element that we describe in here. That is 1837 times smaller than, due to which 1837 electrons equals in mass to the mass of one proton and one neutron. A summary of each of the type of particles, their mass and relative charge is shown in table 3.1. You will see in here. You will notice that the masses of all these atomic particles are matriculated in atomic mass units AMU. This is because they are so light. This is because they are very light, having very little weight, that their masses cannot be measured usually in grams. You can see that is a structure diagram of fluorine atom. 37, 17, 37, 17. We have here 17 protons, and we also have 18 neutrons. In here we have 17 protons and 20 neutrons. Because chlorine 35 is one isotope and chlorine 37 is another isotope. So that's a basic comparison between isotopes of an element. Two isotopes of chlorine, which we have same number of protons but varying number of neutrons. Some atoms and their isotopes. Element, symbol, particle present, like hydrogen, deuterium, tritium. The second one is carbon. Third one is oxygen, strontium, uranium. We have their isotopes and their electronic configuration accordingly. Respectively, you can see in here that cobalt 60 is used in radiotherapy treatment. So cobalt 60 is also an isotope of cobalt element, which we use in radiotherapy using radio imaging, in which we use cobalt 60. So that's the basic explanation of the application of an element belonging to atom. It is a basic explanation to a mass spectrometer. How do we know isotopes exist or not? They were first discovered by scientists using a apparatus called a mass spectrometer. Figure 3.6. You can see the first mass spectrometer was built by the British scientist Francis Aston in 1919 and enabled scientists to compare the relative masses of atoms accurately for the first time. Let us move towards the diagram. We have ionization area, then we have the acceleration area of electrons, then we have drift flight region, where we also measure the time of flight, and drift region, vacuum chamber, inside vacuum chamber. Afterwards, the last one portion is ion detector, which will detect the ions presence, if present or not. So that was a basic diagram of mass spectrometer 3.6. Afterwards, we have a vacuum that exists. Afterwards we have vacuum. exists inside the mass spectrometer. You can see vacuum chamber. Inside the mass spectrometer we have that one. You can see the explanation. There is a +1 charge with each ion. The positive ions are then accelerated towards the negatively charged plate. Yes, that's right. After they cross the ionization area, drift area, and flight region, the spectrometer is set up to ensure that when the ions leave the acceleration area, they all have the same kinetic energy regardless of the mass of the ion. This means that the lighter ions travel faster than the heavier ions. Effectively separates the ions accordingly to their mass. Having left the acceleration area, the time for the ions to reach the detector is recorded. The detector counts the number of each of the ions which fell upon it, and so a measure of the percentage abundance of each isotope is obtained. A typical mass spectrum for chlorine shown in figure 3.7, you can see it in here and can discuss it with yourself in detail. Afterwards, the thing we have is the relative atomic mass. The average mass of a large number of atoms of an element is called its relative atomic mass. Its symbol is S subscript R. This quantity takes into account the percentage abundance of all the isotopes belonging to a particular element if they exist. In 1961, IUPAC recommended the standard used for the S subscript R scale, that was carbon 12. We took a carbon 12 sample was taken which has a mass of 12 atomic mass units. The relative atomic mass of that element is the average mass of the naturally occurring atoms of the particular element, where C12 has a mass of exactly. Afterward discussing a detailed overview over the historical background of IUPAC and carbon 12, we have average mass of isotope of the element divided by 12 mean the relative atomic mass. Mathematical explanation, then we have proper example on it, in which we put it all of the values of the required. We got the original relative atomic mass of the chlorine 35. Calculate the number of neutrons in the following question, which you will do on your own and submit it to my YouTube channel. Okay. Afterwards, the last thing that we have is the arrangement of electrons in atom. So you can see the explanation. The proton, neutrons inside the nucleus. Subatomic particles, which are electrons, move around the nucleus at greater distances from the nucleus through electrostatic force of attraction bonded to the nucleus. And the reason behind electrons circling around is the positive charge inside the nucleus. Rutherford provided the example that electrons evolve around the nucleus in such a way that the orbits around the sun. We don't have exact position of electron in energy level. We say that the place where there is a greater probability of an electron around the nucleus, we call that place high percentage of electron. We have that place as the energy level of an electron or orbit. However, we can say that electrons can only occupy certain definite regions, levels, and that they can not exist between them. Each of the electron energy level can hold only a certain number of electrons.